Alrighty then, corn children. It's time for another fine lesson on vertical asymptotes. Da, 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 da. Alright, so this first bit of the notes, you're going to want to pause it, copy it down, put it into your notes. You know the drill. Alright, here we go. Ooh, look how pretty! A function f of x has a vertical asymptote at the vertical line. Notice it's not y equals, it's x equals c. X equals c. If the limit as x approaches c, now the notation here is a little crappy. It's either from the right or the left on this function approaches either positive or negative infinity. So if on either side it goes up to infinity or down to negative infinity, booyah, you have yourself a vertical asymptote. I want you to remember a little bit of vocabulary. This is a type of discontinuity. It's where our graph is broken. Yeah? All right, it's an infinite discontinuity, an infinite vertical asymptote. All right, now we're going to be exploring vertical asymptotes because the problem is going to be, how do we come up with the location? I mean, if you have a graph, you can go, poop, there it is. But what if you just have a function and you want to know, where is there a vertical asymptote? How do we find this x equals c? So we're going to explore this by considering rational functions. All right, so let's be clear here, or at least I'll try. A function is a rational function if it has a polynomial in the top and a polynomial in the bottom. So I'm not looking at exponentials at this point. I'm not looking at anything bizarre, just a plain old rational function. Most of our guidelines here for rational functions will extend with some exceptions to other functions. So rational functions. All right, so let's look at an example. Nope, let's look at a definition. Totally forgot what came next. All right, so here's the idea. If I can fill in a number into this rational function, and as a result of plugging in the number, the numerator is not 0, but the denominator does become 0. And we know we're not allowed to divide by 0. That's going to cause a discontinuity. But it's a specific kind. Not 0 over 0 with a rational function means x equals c, the number you filled in, is where you have a vertical asymptote. So our job is going to be, look at the function, find out what makes the denominator 0, but not the numerator, and booyah, there's your vertical asymptote. All right, so let's look at an example or two. All right, here's our first example. Put that right there. Find all the vertical asymptotes for this function. It is a rational function. We have a polynomial in the top and a polynomial in the bottom. All right, vertical asymptotes. I want to know when this graph is broken in a very specific way, not 0 over 0. The first thing you're going to want to do is look at the denominator and ask yourself, what would make the denominator equal 0? Well, I'm pretty sure you can figure out that if we turn x into a 1, 1 minus 1 would be 0. So here's the idea. I am purposely choosing to break this function. I'm trying to fill in a number I know I cannot fill in. When I fill 1 in, the numerator is 5. The denominator is 0. This is undefined, but it's broken in a specific way, not 0 over 0. That right there tells me something. Now don't get confused. The vertical asymptote is not at 5. The vertical asymptote is at the number that caused the train wreck. I now know that f of x has a vertical asymptote at x equals 1. Yeah, I know. And if you go back and you look at our lesson on horizontal asymptotes, and if you were to take the limit as x goes to infinity on this, and you would see equally dominant terms, you would know that there's a horizontal asymptote at 2 over 1. Yeah, that's a little review for you. If that didn't make any sense, go back and watch that video. Yeah, that's right. Well, this was easy. All we had to do was look in the bottom and say, hey, what makes it 0? And then we plugged it in. We got not 0 over 0. Boom, vertical asymptote. All right, well, that was almost too easy. I know. Let's do another example. It's harder. Awesome. Here we go. Here's our next example. Find all the vertical asymptotes for f of x equals blah, blah, blah. Again, polynomial over a polynomial. All right, here's the deal. I want to know what makes the denominator 0. Oh, it's all scary. Here's what you're going to want to do. You're going to want to factor. Now, for some of you, that is quite an adventure. I'm just going to factor the denominator, putting it under here. Factors are x and x, factors of -6, positive and negative numbers, 1, 6, 2, and 3. We need to make a -1. So that's going to be a -3 and a +2. So when I look at the denominator in factored form, it's pretty clear to me that there are 2 values that cause the denominator to equal 0. 3 and -2. So we're going to look at these separately. All right, when I fill 3 into the denominator, it does cause the denominator to be 0. But that's not enough to know it's a vertical asymptote. I also need to take 3 and fill it into the numerator. Now, I've already done the work. I think I did it right. And I got 40. Hey, look. Not 0 over 0. Boom! Vertical asymptote. This function has a vertical asymptote at x equals 3. Done. Done. That's it. Vertical asymptotes, very straightforward. If you can arrive at not 0 over 0, you're good to go. Now, what about this -2? Maybe there's a second vertical asymptote. When I take -2 and I fill it into the function, yes, we already know it made the denominator 0. 0 times anything is 0. But here's what's crazy. When you fill -2 into the numerator, it is also 0. Dun, dun, dun. And here's what we know. Absolutely nothing. 0 over 0 doesn't make any conclusions yet. We don't know. So we are going to have to dig deeper. When I see 0 over 0, I think to myself, dig deeper. How are we going to do that? Ladies and gentlemen, it's a cliffhanger video. You're going to need to wait for the point discontinuity video to come to a theater near you soon. And we will discuss how do we handle 0 over 0? When does this become a vertical asymptote? When does it become a point discontinuity? I know, you're all excited and you can't wait.